you for this introduction. Thank you for committee for inviting me, and for Dr. Zhang, and for all of you to stay here with us on this very last presentation. It will be very, well, I hope so, a brief message. I divided into two parts. The first one is about, it's a small repeating of the previous presentation, but from different angle. And the second part is actually the nuclear transfer procedures and how we pick them and what the differences between them and all. And we'll watch some movies, I guess. So,
okay.
Yep. So everything starts from the oocytes, and you've seen this slide before, but I want you to pay the attention on this syndrome. So how actually the embryologist could say that some patients need the nuclear transfers? Well, we use our eyes and brains sometimes. So if we have a patient with a recurrent oocyte maturation failure and independently from a stimulation cycle or what our gynecologist says to us, we can see that the patient has the only immature oocytes, GVs or M1, and you can help them. You can only offer the oocyte donation to such patients, but some of them wants to have genetically related children, so the only option for them is just nuclear transfer at GV stage or M1 stage respectively to the oocyte maturation failure. But there is another option. Some of you have heard it yesterday from Dr. Zhang's presentation. We had the case when the patient, she has almost M2 oocytes. So her oocytes can undergo through the second meiosis, so everything is normally from first meiosis, sorry. So she has like M2 oocytes, but without M2 spindle. So they form not the spindle, but the nucleus already. So we have only polar body and a nucleus. It's like parthenogenesis activation of her oocytes, and it happens to her recurrently. Each time she has a stimulation, we have only such kind of oocytes. So it's another type of maturation failure, because her oocytes cannot stop the process of, cannot be arrested at M2 stage. So we need to propose her go back to the maturation and propose her to make like M1 spindle transfer or GV transfer, or we can use polar body transfer. So here is another repeat from previous presentation, and the only purpose of this slide is just to show you that there are a lot of things to do in oocyte, and if you have a breakage in any step, you will have the problem, and you will have this oocyte maturation arrest. So regarding to the point of this breakage, it can be here, so we propose a GV transfer. It can be here, we can propose M1 or GV transfer. It can be here, so we can propose M2 spindle transfer when the oocytes, they cannot be fertilized. We had this patient, she was 39 years old, and I will return to her a bit later. We had the patient 39 years old with the absence of fertilization. She has a lot of oocytes during her stimulations, but none of them could be fertilized. So we had this M2 arrest of her oocytes. But after nuclear transfer, we've achieved a normal fertilization rate and normal blastulation rate, but unfortunately all of her blastocysts were aneuploid due to age. But we'll return to her a bit later, if you'll remind me. Okay, so the point is, if you have a breakage anywhere in this table, you will have a problem with patient and a problem with oocytes and problem with oocyte maturation arrest. And regarding to the place, you will propose to patient different type of nuclear transfers. So it's just to show you that we know the mutations that cause GV transfer arrest, and probably we can help such patient to restore the ability for maturation of their oocytes. And what about embryos? Just the same. We have, well, now we know that there are some genes, and Dr. Zukin just told you about them, that cause the embryo arrest. So you have a normal M2 oocytes after your stimulation. You have normal fertilization, but then you can have something. You can have some problems like absence of cleavage or abnormal cleavage or absence of blastulation. And the last one is the most common thing among patients that embryologists face in their labs. So when you ask any embryologist, I don't know, how many embryologists are here? Well, quite a lot. So, well, it's surprisingly for me. So when you see the patient with a recurrent condition that you have a normal fertilization, normal cleavage rates, but no blastocyst, it means that this patient has like an embryo arrest, and probably if we will change some stimulation cycles protocols, and the picture will be just the same, you can propose to this patient or offer to this patient to undergo the nuclear transfer procedure. Maybe it will help her, unless it's advanced maternal aged patient. So you've seen the video, and that's our second patient who delivered a baby. So embryos should look like this after 5 days of culture, and embryologists, the vast majority of embryologists here, very familiar with this picture. It's a normal blastocyst, day 5 blastocyst. And if you culture the embryos for 5 days and you see such pictures, so it means that it's an embryo arrest, and we can change it by nuclear transfers. Another reason is, well, there are a billion of reasons, and until now we don't know, and we cannot know all of them. What actually causes embryo arrest? Probably it's some in genetics. Probably it's oxidative stress. Probably it's like chromosomal aneuploidies, but it's very common for advanced maternal aged patients, because when you have like multiple chromosomal aneuploidies, the disproportion of gene expression can cause embryo arrest. But with these patients, it's not so many options we can propose for them. And again, for oocyte, we have this subcortical maternal complex that has a lot of different actions on oocyte. It can be oocyte maturation arrest or fertilization failure. So, yeah, just the same. And just to show you where it works. And these genes are expressed only for oocyte. So the trick here is that the donor oocyte is it has sorry. Okay, so the donor oocyte has all these proteins that are normal, and everything is fine with the donor oocyte. But the patient oocyte has like defect in some of these genes, for example, and it cannot handle the normal embryo cleavage. So when you put the normal karyotype or genetic material of a patient inside a normal cytoplasm, you restore the ability for embryo to normally cleave. So that's the point. Yeah, at the end of part 1 of this short message, So yeah, we know as embryologists that there are some patients with such problems. We face, well, the percentage of them is very low, but still they exist, and in an amount of the whole planet, there are like hundreds of them or thousands of such patients that we can help them if we know the reason or the cause of their problem. Unfortunately, for now, we don't. Maybe in 50 years, we will know all the reasons for oocyte maturation arrest, fertilization failure, or embryo arrest, but now we don't know them. Until we try, we don't know even can we help for these patients. Yeah, but at least for some reasons, we know them. We know some reasons, we know some genetical reasons, we know and there are panels now for patients. We can offer for patients the panel for genetic testing. We can offer them to give their blood, and we can answer if they have, for example, mutation in 2UBB8 gene, we can say, okay, you have no other option except oocyte donation or nuclear transfer that can help you. And we know it for sure because we had a baby after this. And answer to your question, sorry. Yeah, we have removed this mutation from the population because we had a mother with 2UBB8 and her daughter is completely healthy without this mutation. But it's not like changing the genome. It was just 2 copies of the healthy gene she inherited from both mother and father. So yeah. And yeah, the problem starts when you're telling about maternal age, because you know that well, now it's quite obvious that we cannot rescue the aneuploidies. We cannot repair the aneuploidies of advanced maternal aged patients, and I'll show you it a bit later. So the second part, that's probably the most interesting. Now we have 7 types of nuclear transfers. 7. Probably in some years someone will invent even more, I don't know, but my fantasy stops here. Because previously, several years ago, there were 6 types of nuclear transfers, but our Chinese colleagues, they invented the prepronuclear transfer. I'll show it a bit later. So I divided it into 2 major groups, like before fertilization and after fertilization. But before fertilization, we have immature cells, like GV, M1 cell, and mature, M2 and polar body. After fertilization, it's a bit tricky, prepronuclear transfer, polar body second, and pronuclear transfer. So that's my favorite phrase here. The basic principle of all nuclear transfers is just the same. You need to cut and paste. So you need to remove the genetic material from your donor cell and throw it away somewhere, or even keep it, and put the genetic material of a patient inside a donor cytoplasm. And that's all. It's a basic principle for all types of nuclear transfers, and briefly we'll see the schemes for each of them. So for GV transfer, cut and paste. Again. The trick here is to provide the in vitro maturation for these oocytes, and I can say that even in one step, even with a very low efficiency of IVM or culture in the GV cells, we have the euploid embryos. But the problem here is that this embryo we obtained from reverse reconstitution. So we've used the old cytoplasm and young nucleus, and we have still the euploid embryo. But the direct reconstitution, like with old, it's advanced maternal age nucleus, and a young cytoplasm, we had some blastocysts, but all of them were aneuploid, and that's a very common thing for such patient. For each type of nuclear transfers, I have these 2 points, advantages and disadvantages. For GV, to have the competent GV, you need a proper stimulation, because when you accidentally have spontaneous GV after your stimulation, they're incompetent. And as you probably heard yesterday, very crucial to have in this GV a perivitellin space, because all oocytes, all GV oocytes without this space are incompetent. When you culture them, they will die. When you try to reconstitute them, they will die. So you can use only competent oocytes with perivitellin space, and to obtain such oocytes, it's a huge trick for gynecologists or reproductologists to obtain this, to stimulate properly, to have the normal number of oocytes, of competent GV oocytes that you can work with. And yeah, IVM, it's inefficient now, unfortunately, but until now it's very inefficient method. And yeah, you should be very careful with manipulations because they're very fragile. But the main disadvantage of this method, but it's a disadvantage only for advanced maternal aged patients, because for young patient there is no such disadvantage, but for advanced maternal aged patient it's this. Unfortunately, we know that the signal of double strand breakage in DNA. And when you look at the young, it's a donor oocyte, young donor oocyte, and the signal is very weak signal here. So there are no DNA breakages here. But for old, well, it wasn't me who write down this old, it's AMA, advanced maternal aged patient, we can see that the damage in DNA is already huge. So it means that for such patient, probably the GVT is too late. We need to go right a step before GVT, or GV, a step before GV. So the first video. Then we'll move much faster. The same basic scheme, some videos, but everything the same. So now we removing the, oh, sorry. Can you play it again? No, back. Yeah. Can you play the video? Okay, thanks. So removing the nucleus from patient's GV. And as you will notice, the cytoplasmic drop around the nucleus is very small, so it contains very small number of mitochondria. And answering to another your question, well, it's quite possible to destroy them.
This looks painful.
No, it's a video problem. It's not
martial arts.
Yeah. This trembling is a video. It's not my manipulation. It was very tight. Actually, it's very gentle. So, and you can see the cumulus cells here, which are necessary for proper IVM. And you know they're pain while you perform this manipulation because they're messing around and they prevent you from making this procedure right. So that's all. And one, I will show. So, and that's where I've tell you about this 39 years old patient that had aneuploid embryos, because that's her case, and that's very interesting here. after PNT, this type of nuclear transfer is my favorite, and I like it much more, with the time even more. So I think that this type of nuclear transfer will be the future that I will focus on, because it works very well. It's much more easier to perform this type of nuclear transfer than M2 nuclear transfer, because you don't need to get rid of a polar body from donor cell, and the spindle is very big, so it's very handy to remove it from the cell, and all the other steps are very simple and handy. So you can all you need to do here is just to make these transfers, perform such not so complicated maturation, and then just fertilize them and wait until you have blastocyst and have a baby. So and now we know that this method works, and it works very good, because the blastulation level is just the same as it is in a control group. What I wanted to show here, and that's interesting, that I was thinking that, okay, we have this impaired spindle of advanced maternal aged patients. So what if we will just destroy the spindle completely and let the donor cytoplasm to reconstruct the spindle by itself, by its own forces? And that's what I did. Here you can see the control oocyte. That's a M1 spindle that was taken off from cell right after reconstitution, and M2 cell. So here you can see the very weak signal, and I improved this method, and there is no signal right now. So you destroy the spindle completely, the spindle of a patient. There is no protein in it, just disassembled chromosomes flying around. And then after reconstitution, as you can see, the donor cell just reassemble the spindle, and it looks very nice. And then it matures very well and fertilized very well. And you know what? For this 39-year patient, we had, before all of this, we've made like pronuclear transfer for her. We had multiple aneuploidies. After this procedure, we had only one aneuploidy. It was minus 12 chromosome. So we, in some sort, for some percentage, we have improved. Well, it's not enough data to make any conclusions, but still it's very promising. Okay, so you know this, because it was the first baby born in the world after nuclear transfer, this method. It works very well. We have another baby from Nuno groups. We have some ongoing pregnancies in the world after this procedure, so there will be more babies after this. And yeah, well, it's quite a good procedure. Just let us see the... It's for both of them, for M1 and for M2 spindle transfer. So you definitely need the polarization microscopy. And you need the proper timings, because your ooplasm could be spoiled with the time. And there is a problem with spontaneous activation, and another problem that's not here, it's a cytoplasm leakage, and Nuno will tell me the secret, how to prevent it. Because when you open the zona pellucida, there is a tension in it, a huge tension. It forces the cytoplasm to leak out of the holes that you create. So with a patient cell, it's not a big problem, because you need only a spindle, but for donor cell, you can lose the cell. So it's the thing that you do not prefer to have. But the spontaneous activation, it is a problem, because they're like loaded. These cells, they are prone to be activated, and it could happen even to M1 cell, which will create even 2 PNs or 1 PN, huge 1 PN with 96 chromosomes in it, but they can be spontaneously activated. This slide is just to show you that when you remove the spindle out of cell, in a light microscopy, you can see the chromosomes. Well, here I can see them very well on the screen, but you can see these black dots are chromosomes, and you can see them in a light microscopy. It's some sort of a miracle. But there are yeah, you can see it. There are publications that say that while you perform an M2 spindle transfer, you will have the abnormal fertilization. It's much higher than in a control group, but that's not that we've observed or see in our experiments. Well, we've performed this procedure under proper conditions, so we have a normal fertilization rates, normal blastulation rates, and so on. So I think it depends on conditions under what you perform this procedure. So yeah, the principle, just as I told you, cut and paste. Just cut from patient cell and paste to donor cell. That's all. And you'll have a baby. There are different types of polarization microscopy. It's only one of them. Okay. So, and my second favorite one, because we have 10 children after this procedure, let's go to advantages. Well, you need less cell to work with because they're already fertilized cell, and when you perform the fertilization, some of our sites will not fertilize, and some of them will probably will be dead after fertilization. So making the PNT, your work with a lower number of cells. So it's a huge advantage for embryologist. But there are a lot of questions that we don't have an answer on them. How this procedure impact during these processes that occurs inside the pronuclei. We don't know, but apparently we have 10 children and they're healthy, so probably there is no impairment in this, but who knows? We just don't know. And the centrosome is another point, because centrosome is attached to female PN, and you can accidentally remove the centrosome with the pronucleus. So it means when you remove from patient cell the pronuclei without centrosome, and you have removed the centrosome from donor cell, the reconstituted cell will be unable to cleave properly, and it will never form a blastocyst. Or if you put the two centrosomes into one cell, you will have direct cleavage. So it's abnormal cleavage when the zygote cleave to 3 or 4 blastomeres at the same time. So it's not the thing that you want from this procedure. And as far as you cannot see the centrosome, it's a problem. I didn't tremble while I performed this. It's just a video. So I hate tables, so I tried to make these tables as simple as it's possible, so that even I can understand it. Again, there are two groups of patients, above 37 years old and below. And here you can see the overall number of patients here, and here is a number of patients that had embryo transfers. So totally we had 30 patients in both groups and 13 embryo transfers. But look here, for advanced maternal aged patients, the cancellation rate was very high, and for younger patients it was, well, almost zero. So for all of these patients, almost for all of these patients, we performed embryo. We had embryos for embryo transfer, and we made embryo transfers. So look here, the zygotes was comparable. The blastocyst, they were comparable. But the number of biopsied embryos were different, and the number of euploid blastocysts were completely different. So we cannot restore the ability of oocytes to after meiosis. So we cannot repair it. So it's procedures involved because it looks like this process is unstoppable right now. So thank you for your attention.
So, thank you very much, Pavlo. So, this presentation is open, Joe?
So, I mean, it's miraculous. It's just, it's amazing that it works. It's amazing that it's not just the schematic diagram that it works. Two quick questions. Do you fertilize by ICSI?
Yeah.
And do you use nicotazole or cold, or how do you collapse the spindle in the M1 to M2s?
Well, we use cytokalism B for as relaxant, and for fusion we use it's HAVGA complex. It's a Sendai virus. Well, particles.
There are some other microfilament inhibitors.
Yeah, I know.
And I think a lot of people like cytokalism D a little bit better in terms of reversibility, but it works. It's a miracle. Congratulations.
Yeah, thanks.
Very good.
Oh, I have a question for Nuno.
Sorry. Congratulations for your talk. Really nice. I think it's clear that a metaphase to spindle transfer or pronuclear transfer is not indicated for advanced maternal age, and it's just for embryo development arrest, I think.
Or mitochondrial disease.
Or mitochondrial diseases. I think also the results for young patients with embryo development arrest are really nice if they are young. But thinking on the eventual development of a technique that could reduce the incidence of chromosomal abnormalities, you said GV transfer could be an option, metaphase 1 transfer could be an option, and you also said that probably we would need to go before the GV is formed. So if GV transfer is not the option because of the technical difficulties on oocyte maturation, or if, but then you gave some hopes on metaphase 1.
Well,
So
we need to
if
continue.
we need to go back before GV transfer, but you're saying that maybe with collapsing the spindle in metaphase 1, we can reorient the spindle in a better environment, and maybe you could reduce the incidence of abnormalities. So what's your opinion? Which way should we follow?
Yeah, thank you. So the point here is that we can help or repair only some part of a problem. With destroying the M1 spindle and given
one question related to what was asked. How do you destroy the spindle? You have to use antimitotic. Well, I give you mine and you give me yours.
Okay.
No, you probably need to use an antimitotic drug like nocodazole or so, right?
No, well, in this photo it was nocodazole.
Okay. A reversible drug.
But the exposure time was huge.
But which way should we follow? Before GV or before M2, between GV and M2?
It depends on an amount of damage of DNA of patient, because in some cases there is so huge damage to DNA that you cannot repair whatever you try to do this. When you have this smaller amount of DNA damage, or you don't have this linkage between homologous chromosomes that cannot be divided, or you've lost your chiasmus, or you lost the caucasins. You cannot repair this even if you destroy the spindle, because for the young cytoplasm there will be not enough resources to restore the integrity of this spindle. So I would prefer to go before GV, to use some sort of artificial gametes, for example.
Okay. Thanks.
Okay, very good. Last question, please. Yes, go ahead.
Excuse me, is it necessary to use electrofusion in your technique after injection?
Well, there is no other options. Well, when you remove something from the cell, you cannot put it back. It will not be sucked in any way. So you need to use some agent to perform the fusion. We use this so-called Sendai virus, but it's not a virus, it's a membrane part of the virus with the proteins, hemagglutinin proteins. And some other scientists, they use electrofusion for this purpose, but, well, it's up to you to what to choose.
And how did you collect M1 oocytes?
What?
How did you collect?
Well, there should be special stimulation cycle, but it's a question for our doctors, but not for me. I'm an embryologist. Sorry.
Okay, thank you very much. I thank the speakers for this session. Very interesting, new stuff. Very much.